Welcome back to our videos describing the kinematics of rotational motion. In this video, we are going to make a connection between rotational motion, objects that are spinning around a central axis, to translational motion when objects are actually changing their position in space. So when I'm talking about this connection, I'm not going to be talking about objects that are both rotating and translating in space at the same time, like a frisbee. We're not at that point yet, but what I'm going to be talking about is the fact that as this object is rotating, individual points on this object, like these two bugs, are translating in space. They are moving their location also around this central axis, and there is going to be an interesting relationship between how many radians per second these objects are covering and how many meters per second these objects actually have to move. So just to show you what this video is going to be about, if I have this spinning rod here, obviously it is in rotational motion, and this rod is covering a certain number of radians each and every second because it has this angular displacement around this circle. And we have always been looking at the distance it covers in terms of this angular distance. Even though this rod has to rotate around 2 pi radians to get to its original position back at the top, every single point on this rod is covering a translational distance. It is actually moving a certain number of meters, not radians, but meters, around this circle. So the edge of this rod and halfway around this rod, notice, are tracing this exact circular path. They each have to cover a certain distance, which is going to be the circumference of this circle, in order to get back to its original point. Now the thing I want you to notice is that even though both of these points, the edge of the rod and kind of the middle of the rod, both are rotating at the same rate, and they're both covering 2 pi radians of angular displacement, notice the distance that the points actually have to move in terms of translational motion. This path around this circle, they are taking different paths with different distances around this circle. And this is what this video is really going to be about. We are going to be looking at these objects in rotational motion, but as they are rotating, individual points on this rotating object are going to be traveling a distance around the circle. They are going to be covering a certain number of meters each second around this circle, and if they are speeding up or slowing down, then they are also going to be accelerating. And all of this is going to be in a translational kind of frame of reference. But if we look at this GIF here, it makes it obvious that the point on the outside is moving at a faster translational speed than the point on the inside. So the second thing we're going to discuss is why different points on this rotating object are going to have different translational quantities, so covering different distances at different speeds, even though the angular quantities are going to be the same because they are on the same spinning object. So all of the rotational kinematics quantities that we have discussed so far, we have been applying to whole objects. We have been looking at the entire object as one spinning system. So let's say I have this circular object here. It might rotate through a certain angular displacement theta at a certain angular velocity, and maybe it is speeding up and slowing down and has a certain angular acceleration. We have been saying this entire object is experiencing these angular quantities. So maybe the wheel is moving at an angular velocity of 10 radians per second, or the disk is spinning at -2 radians per second. We've been applying these quantities to the entire rotating object. But these quantities can also be used to describe individual points on that object, on that rotating mass that we are looking at. So if I have this spinning disk here, and it has a couple of points on it, so one in the center, one in the middle, and one on the edge, let's say the entire disk rotates through an angular displacement theta. Well, it turns out this point on the edge also rotated through that same angular displacement theta, and so did this point in the middle. Notice if they are moving with the disk, this angle is the same no matter how far away from the center of the disk you get. This angular displacement theta that we have used to describe the entire disk also is describing all points on that disk. In addition, if the entire disk is rotating at an angular velocity, then that means each individual point also has to be rotating at that same angular velocity because it's going to cover the same angular displacement, and it's going to take the same amount of time for this point to rotate over here as it will take this point because they are spinning together on the same object. The same thing is going to happen with the angular acceleration. If the entire disk is speeding up or slowing down, then so are these individual points on the disk. So all of these individual points are going to have the exact same angular values, theta, omega, and alpha, no matter where they are. If the disk is spinning at 2 radians per second, then we would say every single point on this disk is also spinning at 2 radians per second. But translational quantities are going to work a little bit differently. So when I'm talking about these translational quantities, what I'm actually talking about is the actual distance, velocity, and acceleration. So these are our quantities from Unit 1 that these objects are actually going to travel through. So if we look at this disk, if it spins through an angular displacement theta, then this point halfway through to get from here to here has to cover this linear distance that is essentially this arc length. On the outside, this point has to cover this linear distance. Notice points further away from the center had to cover a greater distance to get to the same angular displacement. The further away we get from the center, the larger this arc length is going to get. Since all of these points are also spinning on the same disk, it's going to take them all the same amount of time to reach this second location. So that means all of these distances are being covered in the same amount of time. Since the point on the outside has to cover a greater distance, then that means it is going to have to be moving at a greater velocity, at least a translational velocity. Again, the angular velocity was the same, but it is covering more translational distance because it has to go around the outside of this circle. It's going to have a larger circumference to cover. So even though we just saw all of these points having the same angular quantities, all of these points are actually going to have different values for their translational quantities. How much distance they cover, the translational speed they move at, and also their translational acceleration. And the differences in these values are all going to depend on the differences in these radiuses. How far are these points away from the center of this rotating object? So in general, we have a rotating object and there's different points on that object. Points that are located further away from the point of rotation, which is usually the center, are going to be moving at a faster translational speed. That's because they have to cover this outer circumference, which is the biggest circle they could possibly cover, or on the inside, points closer to the center of rotation only have to cover this smaller circle. They are doing it in the same amount of time, so the object that covers the greater distance in the same amount of time must be moving faster. The further you are away from the center of the rotating object, the larger your translational quantities become. So it is both distance, speed or velocity, but also acceleration. But again, just to remind you, all the points will have the same angular quantities, but the translational quantities are radius dependent. And there actually is a directly proportional relationship between your distance from the center of the rotating object and these translational quantities. So if we have a point on this spinning object at R1, is going to have a translational speed of V1. If we have twice the radius, we're going to have twice the velocity, 3 times the radius, 3 times the velocity. Now, knowing our angular quantities, if we know how far the object spins, how fast it's spinning, or how fast it is accelerating, there is a way that we can then essentially translate to these linear quantities, as long as we know the key connection between these two, which is going to be the radius. As long as we know how far the entire object displaces, we can figure out how far a point on the object is going to displace by using this equation. Same thing, if we know how fast the entire object is rotating, we can figure out how fast a single point on the object is moving translationally, as long as we know its distance from the center of that axis of rotation. It's called r, a radius, but the true definition is it's how far away it is from the axis of rotation. Keep in mind, it's not going to be the radius of the whole spinning object itself. It might depend on where on the object you are looking at. We can do the same thing with the acceleration. We can predict the translational acceleration of a point on a spinning object as long as we know the angular acceleration of the object and how far away from the center of the spinning object the point is. Now, these three equations are not on your AP equation sheet, but they do show up and they sometimes are asked for you to be used on questions. So here is how you can derive them. First thing you have to remember is that the connection is the radius. All of these quantities, these linear quantities, are radius dependent. Further away you get, the larger these quantities get, so keep that in mind. But if you're trying to decide between these two equations, essentially, which one do I need to multiply by the radius? Am I multiplying the angular quantity by the radius to get to linear? Or am I multiplying the linear quantity by the radius to get to angular? I recommend you always look at units. The distance has to be in meters. Angular displacement technically actually doesn't have units. Radians aren't really a unit, even though in physics we treat it as units. So notice the meters are on the left and the right side of the equation. It's going to balance out. If you accidentally write it like this, then you're going to do a radius in meters times a distance in meters, and you're going to get radians is equal to meters squared, which definitely is not something that is going to work out. So always keep in mind you want your linear quantities on opposite sides of the equal sign. So up here at velocity, you want meters per second over here. Radius is going to be in meters, and then your angular velocity is going to be in radians per second. So here is how you get meters per second on either side of that equal sign. But I would just take some time to memorize these three equations. They are quite useful. All right, so in your notes on page 214 are 5 quick examples that I want you guys to try on your own. Some of them are review of rotational kinematics problems, and some of them are going to be applying these new equations using that distance from the center of rotation to predict the linear quantities. Try those on your own, and then on my website you can check your solutions. So in summary, when we're looking at individual points on a rotating object, it doesn't matter how far from the center of that object the individual points are. All of these points are going to share the same angular kinematics quantities. So the angular displacement, angular velocity, angular acceleration are not dependent on their distance from the center of the object. The translational quantities, however, are dependent on how far away these points are from the center of the rotating object. The further away we get from the center of that rotating object, the more distance that point is covering as it travels around the circle. So the faster it has to move, the faster it has to accelerate in order to keep up with the other points on that circle. And we have these equations that we can use for a quick translation between the rotational quantities for the object and the linear quantities for a single point on that object.